like you superimpose this one value to all of them?
Oh.
Yeah.
Or like change in cortisol level?
And then I saw
And then this one
that.
is labeled on, but it's just cortisol level.
And that happened all.
Okay.
While I was
I think that graph is pretty unstable. Yeah, you can't.
Like you can make it slightly better if you change your alpha. But your alpha is like 0.2, you can change it your dots. So where is the line that you put your points?
Like this one?
Basically,
That's like what this graph is.
Hi there, I am.
so instead of saying like value
Are you doing in June font more so?
yeah, it has
It's
to
the government.
But like regardless, I think paling it.
The government is PC.
Palin.
Yeah. Is there a way to different colors and different panels though?
So just, honestly, it looks like the same line as, or like, should we make something
Line or we'll check that it's like.
How was it?
I mean,
Yeah.
if the best fit looks like it's one.
But like area, which is like whether
It's
it's
a
a single
fleet
bird,
vehicle, so
one
one
first,
first,
1
one
second,
second,
4 years, and then 10% outside.
It's a 2017. You're trying to do
What's your response variable? Cortisol level. And then
This one? Or one? Again? I think yes, you played.
oh, there we go.
That's the Paris.
nice. Yeah.
So what did you change?
I ran it again and did conditional instead of contrast. But now it's like underneath the data.
That's okay, you just change the
And then I
order.
can play around.
You changed these.
Yeah, so it's just the order you have to do. It's the order that they show up. So if you have your
The points. After that.
I think it's like instead
There's
of
a-
This is what he has.
So what happens when it really falls?
yeah, sorry, it's not great.
And by the time term ends, I'll have this figured out.
No, it didn't.
Oh, it doesn't have the predictor. Yeah.
It's not really a very convenient location to have the controls.
especially because the remote doesn't work at all.
I know, this,
It's just like the order.
Oh, like,
I've never
Yeah,
found
no,
one that
what
works.
I mean is if you could
So to answer your question, yeah, we face this all the time,
swap
and
your
we
second and third.
wrote our undergraduate textbook on how to deal with the p-value problem. And if you read the book carefully, you'll see that we never base that conclusion on a p-value alone.
Yeah.
That's something that we try to do. Mike and I are
Not like.
Yeah. I definitely like the way that you guys teach the statistics class a
Yeah,
lot
like you're just
better than
building,
the way I was
right?
taught
Isn't it just like the earlier
statistics in
version?
my undergrad.
How do you say that? You're great just without the Oh, you have a question?
I do.
Okay. Nothing wrong, I just don't understand.
When you're doing the mixed effects model, how would you add a covariate?
Well, covariate is just something else that's in the model. So it would be just fixed effects.
Okay. Second.
Okay, so you just
That's
do
when,
like.
oh, it's those are three different.
So a covariate would be usually
Yeah, yeah, so
like
the only one you want.
continuously varying point. That would,
But that has the.
yeah, random effects are always categorical.
Oh, so we're modifying that.
Yeah, correcting the body cells or something like that. That would be helpful.
So you just do times.
Alright,
body
Or,
size.
yeah, again, how you actually model that is in there's an added term or other interaction with other things. That's separate questions.
Play color.
Yeah.
Which comes back to
Great.
Okay, let's get started. Everybody here. So at several points in the course so far, we've dealt with the shortcomings of particular methods or critiques of particular methods. And often the idea has been mentioned that, oh, if we only do Bayesian statistics, our problems would be solved. And I think now is the time that you're ready to actually address the question, what is it? And how does it work? And does it actually solve all the ills of conventional statistical methodology? So I'm here today to tell you the answers to these burning questions. And I'm going to focus mostly just on some of the fundamentals. I'm not going to go in great detail as to how one actually carries out an analysis using Bayesian statistics. For example, how does one calculate the equivalent of a two-sample t-test using a Bayesian procedure? I've met a number of statisticians, those in the statistics department here, for example, and they all do sort of mathematical statistics theory stuff, and they're all Bayesians. And I remember I asked them once, well, if you're all Bayesian, why isn't it easy to do Bayes statistical analyses on the computer? Like, why is it still so easy to do p-values, and yet all the statisticians are saying it's no good? And actually, there are methods now where you can do Bayesian analyses, but it's still not as easy for some reason as just doing something like a two-sample t-test. I think there's a package called Bugs, which connects to R, that you can do a lot of these methods in. But first, let's talk about what exactly is it that we're doing when we employ Bayesian statistics. And I want to start right at the beginning, and that is to ask the question again, what is probability? And I guess the question I want to ask first is, what is it for? And the answer is, well, it's kind of a mathematical framework that we use to quantify uncertainty. And that's its main use, that we allow ourselves to put a number that's on a scale of 0 to 1 to reflect just how certain or uncertain we are about a particular problem, the answer to a particular problem or the state of the world in some way. And the mathematical theory that underlies all of the statistical methods that we use were developed to model outcomes in games of chance, gambling. So even though this is a highly respected field, we have to remember that often it was through dubious motives that many of the methods were actually invented that we use all the time. And certainly in games of chance, it's the long run outcome that we're primarily interested in. If you're playing blackjack, you really want to adopt a strategy where the probability of winning is high, and that probability is defined as the proportion of times that you would win in the long run if the same random trial would be repeated over and over and over again, and each game would be represented as the same random trial, the same deck of cards, and so on. And then a probability distribution is the list of all mutually exclusive outcomes that might occur and their probabilities of occurrence. So the definition of probability, and the one that's used in conventional statistics and the one that we've employed so far in this course, is it is a frequency, a long-run frequency. And there are a number of probability statements that I can make that make sense under this definition. If we toss a fair coin, what's the probability of 10 heads in a row? It makes sense to us. We have this idea that a coin is probably fair, and that if we flipped it in the long run, the probability of heads would be 0.5, and each toss is independent, so we can actually calculate this using the binomial distribution. More complicated kinds of probability, uses of this concept of probability. If we assign treatments randomly to subject, what's the probability that a sample mean difference between treatments will be greater than 10%? Those are the kinds of questions that we ask when we test null hypotheses or when we estimate confidence intervals. We can always use, we can always phrase it in terms of biological problems as well. If we model a process of genetic drift in a small population, what's the probability of fixation of a rare allele? We can make that because we recognize that every generation represents another random trial. And so we can use a model where the probability is defined as a frequency. And then our favorite, of course, the one that was up for discussion today. What's the probability of a result at least as extreme as that observed? The null hypothesis is true. This is the p-value, much derided by Bayesians and even ourselves. And in all these situations, particularly those involving sampling data from a population, sampling error is the sole source of uncertainty. But here are some probability statements that you might hear used all the time, but they represent statements that use the word probability to refer to uncertainty, again, but our definition of probability makes no sense in this context, or these statements make absolutely no sense in terms of the probability definition that I just gave you. What is the probability that Iran is building nuclear weapons? Well, you ask yourself, well, first of all, what's the random trial here? Are there multiple universes? In each of them there's a planet Earth, which has a country called Iran, and in some probability of those universes, Iran is building nuclear weapons, and in the other fraction they are not. That's pretty stupid. This statement is about uncertainty, but it has nothing to do with frequency. What's the probability that hippos are the sister group to whales? What do you mean, what's the probability? Either they're the sister group to whales, or they're not the sister group to whales. There's only one group clade that includes the hippos and another the whales, and the uncertainty here doesn't arise from any random trial. It arises from our lack of knowledge about this, maybe a limited amount of data that we've been able to gather to determine the answer to this. So again, either Iran is building nuclear weapons or it's not. The statement about probability makes no sense in terms of frequency, but it does reflect something about our uncertainty about whether the statement is true or false. I'm going to go through an example, but in a more prosaic sort of situation, one more close to home would be, what's the probability that the fish sampled from that newly discovered lake represents 2 species of stickleback rather than 1? So we can make statements like this all the time, and the probability in this context here, again, makes no sense by the definition that we gave it already, even though here we understand that it's saying something about our uncertainty. Either there are 2 fish in that lake, or there's 1, and it's really up to us to figure out which is which. There's no random trial at all. I thought about this one periodically. What's the probability that polar bears will be extinct in the wild in 40 years? And I can't really decide whether that use of the term probability here does or does not make sense with the definition of probability as a frequency. It is possible to model a series of random trials in the future and then calculate that, it might be difficult. So why they don't make sense? Either there isn't. There's no random trial. Either they are or they aren't. No random trial. Either there's 1 species or there are 2. There's no random trial. Maybe there are random trials. You can think of future outcomes as being determined in large part by chance. And in some of those outcomes, polar bears go extinct, and in some that do not. But what's different compared with the probability definition that we conventionally use is along with frequency. In all these statements, probability is used to represent uncertainty, but the source of uncertainty is not sampling error, it's information. It's how much we know about whether or not Iran is building nuclear weapons. It has nothing to do with frequency. And this is important because information being the source of uncertainty means that it's subjective. This is subjective probability. The information you have is different from the information I have. And so we would put different numbers on this question if we absolutely had to. And that just seems weird. So this is the alternative definition of probability. It's a measure of degree of belief associated with the occurrence of an event. Let that sit for a moment, and then I'll repeat it. I see faces scrunching. What? I had no idea. Probability is a measure of degree of belief associated with the occurrence of an event. And that's how Bayesian probability is defined and how it's modeled. And we put our uncertainty on the same scale of 0 to 1, and in fact we use the same in large part mathematical machinery to compute probabilities as we do under the completely alternative definition that we normally think about when we analyze data. A probability distribution in this case is a list of mutually exclusive events and the degree of belief associated with their occurrence.
So you're using belief and certainty
Information.
interchangeably?
Yeah,
Okay.
information.
All right.
But it's a subjective thing. It's how uncertain I am.
Right, okay.
So we also realize, we see them all the time, that Bayesian methods are used increasingly often in ecology and evolution. And Mark Mangle, who with Colin Clark wrote a book on analysis methods in behavioral ecology. He just said to me one day, ecologists are facultative Bayesians. Sometimes they'll use conventional definition of probability, sometimes they'll use a Bayesian definition of probability, sometimes this will happen in consecutive paragraphs. And absolutely no one will fall off his or her seat when this happens. And maybe it's not even, maybe it's the case that the author isn't realizing that the completely nonsensical or completely different definitions of probability are being used in those two cases. Dennis has sounded the alarm, however. Ecologists should be aware that Bayesian methods constitute a radically different way of doing science. Bayesian statistics is not just another tool to be added to the ecologist's repertoire of statistical methods. Mangle says that's exactly what ecologists are doing. Instead, Bayesians categorically reject various tenets of statistics and the scientific method that are currently widely accepted in ecology and other sciences. Is it dangerous? Should we be using it, or should we stay away? Well, it depends. I've had discussions with my co-author, Mike Whitlock, a lot about various subjects related to statistics, and one is the definition of probability. He just thinks we should just, everything would be okay if we just didn't call it probability, we should call it probability. And then there would be no argument. Not only that, it would be possible to tell which probability the author was talking about when he or she wrote it and used it in the manuscript. Probability in one paragraph, probability or bro in the other paragraph. So an example was already given, but I want to go through it again because I want to translate the harmless form of Bayes' theorem and its use to one which is, or has been, more controversial. So again, genetic testing of a condition which is relatively rare in a population. So Down syndrome. Down syndrome occurs in about 1 in 1,000 pregnancies, so it's not that common overall. And the triple test is still used as the first test, but not an exclusively used test. There are more accurate tests, but they're typically more dangerous. So the triple test is safe, it's cheap, gives some information, and it continues to be used. And so the question is, how does it work, and what can we infer when we use it? I'll draw the sort of events, the consecutive events, in terms of a probability tree, which has certain uses. And sort of the first branch is whether a fetus has Down syndrome. So you're a genetic consultant, and this is the question that you want the answer to: yes, the fetus has Down syndrome, or no, the fetus does not have Down syndrome. And then given the way the probability tree works is that for each of the outcomes of the first trial, there are alternative possible probabilities of outcomes for the second trial. And I'm going to model then, use a tree to model the test results as being yes or no, the triple test results. And then the probabilities of all those outcomes. So here they are. 1 in 1,000 fetus has Down syndrome, and the other 999 do not. And then what is the accuracy of the triple test? Well, it's not incredibly powerful, but it's still used because it says something. But here's what it says. So we know that if a fetus has Down syndrome, there's a 60% chance that it will test positive, that the triple test will give a positive result, and a 40% chance of saying no. So as I said, it's not hugely accurate, but nevertheless useful. If a fetus does not have Down syndrome, however, there is a 95% chance that the test will be negative, and only a 5% chance that the test will be positive. So the convenient thing about a probability tree is that all of the paths from the root to the tip are mutually exclusive sequences, and so you can multiply their probabilities to get the final probability over there. So 0.01 times 0.6 leads to 0.0006, and so on. And because they're mutually exclusive, they must all sum to 1. Okay, so the probability of a positive result from the triple test is 0.6, given that a fetus has Down syndrome. And this is a conditional probability, which is something I defined the other day, and conditional probabilities is all what Bayesian statistics is all about. So what's the probability? What we really want is the inverse of the probability of a positive test result given that a fetus has Down syndrome. What we really want is what's the probability that a fetus has Down syndrome given that the test is positive. And that can sort of be intuitively calculated by looking at the probabilities at the tips of the tree and going, well, what are the paths that lead to a positive test result? And they are this path here and this path here. And so these represent the sort of a population of outcomes in which there is a positive test result, and then the only question remains is what fraction of them actually have Down syndrome. And so that fraction is 0.006 over the sum of those two, which in this case is 0.012, or 1.2%. So the probability in this case that a fetus has Down syndrome given that the test is positive is less than 2%. You think, well, that's just really weird, but it results from exactly what Shahab pointed out in his part of their presentation, and that is the reason this probability is so small is that Down syndrome is so rare. And as a consequence of Down syndrome being so rare, that even though this test is relatively accurate, most of the positives are false in the population that we learned. Okay, so I've shown you sort of intuitively how you can calculate the probability of Down syndrome given a positive test result. And basically what I've shown you is Bayes' theorem. And so that can be formalized using this equation, which is exactly what I just did intuitively. So the probability of A given B, so we're usually able to calculate the probability of B given A, as in the previous test, and the probability of B given not A, but what we want is the inverse. We want the probability of A given B. And that's the inverse that we are interested in, and Bayes' theorem is a formal equation that allows us to quantify that simply in all circumstances. But it's nothing more than the intuitive fraction that I showed you before. So while Bayes' theorem is totally uncontroversial, what has been controversial is how Bayes' theorem is used. And here's an example. So Bayesian inference can be used in a court of law to quantify evidence for and against the guilt of a defendant based on a match to the DNA evidence at the crime scene. And the question that we're interested in is, what's the probability of guilt given a positive DNA match? And that involves an application of the same equation that I just showed you, Bayes' theorem. And we can show the event in exactly the same kind of probability tree as we did for the genetic event. And that is, there's some, let's call P the probability that the defendant is guilty, and 1 minus P that the defendant is not guilty. And let's just say the probability of a DNA match given that the defendant is guilty is 1. Like, it's just absolute. We're going to ignore the possibility that sample contamination has occurred, but the probability of, the possibility of sample contamination has been in the news more than once over the last few years, so this kind of nonsense happens. This is the crud factor. Let's just assume there's no crud for the purposes of this, example. And so then the real question that concerns us is, well, what's the probability of a positive match if the defendant is not guilty? And we can, let's just say again for the purpose of this match, but for the purpose of this example, that it's just 1 in a million. Like, it's incredibly small. If the defendant is not guilty, there's only 1 in a million chance that the DNA test will be positive. And everything, 1 minus 1 in a million is the probability that the test will not be positive. So what's the probability of guilt given a positive DNA match? Application of Bayes' theorem gives us this equation here. Okay, and that's what I'm going to use. And those are the probabilities of all the mutually associated, all the mutually exclusive paths from the root to the tip. So that's P, that's 0, that's 1 minus P, 10 to the minus 6 over this, and then exactly as I showed you for the genetic test, the probability of guilt given a match is this divided by the sum of this and that. Those being the outcomes that lead to a positive result. So, some jargon. In Bayesian statistics, this quantity here is called the prior probability. And the prior probability represents a statement about the probability that the defendant is guilty without having looked at any of the evidence. So that's why it's prior. This makes no sense under the definition of probability that we've used in this course up until now. Either the defendant is guilty or he is not guilty. And so it can be controversial and to put a probability on it, and then if you do, to ask yourself, what exactly does that mean? It represents your subjective degree of belief before you even look at the data that the defendant is guilty or that the defendant is not guilty. After you've looked at the data, the probability of guilt given a match is called the posterior probability, and that's what we want. If that probability is high, you know, buddy goes to the gallows. But if that number is low, then beyond reasonable doubt is not met, and you know, a verdict of not guilty must happen. So then the question becomes, in this case, well, what exactly is the prior probability that the defendant is guilty? And how do we decide that? Especially given that your prior probability that the defendant is guilty might not be the same as mine, because in fact it's a subjective degree of belief. It's based on information, and what information do we have? Maybe you know more than I know. And if you know, we can imagine that this guy was just picked out at random, you know, drunk and disorderly, hauled into the police station. A blood sample was taken and it was put on the the CSI database. Then we have to say that the prior probability that this person is guilty in a town of, let's say, 1 million men is 1 in a million. Why not? Can we say anything other than, are we justified in saying anything other than the prior probability that this person is guilty is just 1 in a million? Because it's a town of 1 million people and one of them is guilty, and this guy just came in off the street. If we plug this value into our equation from the probability tree than the posterior probability of guilt given a DNA match. A DNA match that is accurate 999 times, sorry, well, has this accuracy is only 0.5. So despite a DNA match between this individual and the blood left at the crime scene, the posterior probability of guilt is 50-50. It goes free. And that's despite the high accuracy of the test itself. It's pretty weird. But what if instead we decided that the prior probability of guilt is actually 0.5? Maybe he's guilty, maybe he's not. Since we don't know, let's give each prior 0.5. If that's the case, here's the posterior probability of guilt to the gallows. Okay, so you can see how the probability of guilt given a match can lead to very different posterior probabilities depending on the prior. And so then the question is, how do you construct the prior? I don't actually know what the court of law says about how priors should be constructed. I'd be interested to know. Does anyone have a law degree by any chance? I'll just come back for more. Yeah, it would be interesting. So I ask you, is the defendant guilty or innocent? I mean, the fact is, this is why when the Bayesian inference is used in a court of law, there has to be additional data tying this individual to the crime scene. He was there when the police arrived. Okay, now we're no longer talking about a random person picked up off the street. And then it becomes much more reasonable to use something like 0.5, but you can see how prior probability can determine whether the defendant on trial dies or is set free. I guess if this happens in Texas. Okay, so Bayesian inference with data is the same principle. We have a probability tree and we may have two hypotheses, hypothesis 1 and hypothesis 2. We may have a million hypotheses, but let's just keep it simple for now. Because in fact, we might not be testing hypotheses at all, we might be estimating, and so every range of possible values for a statement portion would be considered here. And what we can say once we look at the data that we have is, what's the probability that we would get the data if the hypothesis 1 is true? What's the probability we would get the data if hypothesis 2 is true? And then what we want to do is get the posterior probability, which flips things around, and then ask, what's the probability that hypothesis 1 is true given the data that we have? So before we launch into that, I want to at least pause for a moment and go, what exactly does that mean? The probability that hypothesis 1 is true. There's no random trial here. And yet, hypotheses are modeled as though they are random variables. There's a certain prior probability that hypothesis 1 is true, and a certain prior probability that hypothesis 2 is true. That basically says that the hypotheses are random variables. And yet this makes no sense in the framework that we're more accustomed to, which is either hypothesis 1 is true or hypothesis 2 is true. It's up to us to figure out which and to gather evidence. Hypotheses aren't the same as random trials. We don't have parallel universes in which some fraction of those universes hypothesis 1 is true, and then the other fraction hypothesis 2 is true, and we happen to be sitting in one randomly chosen universe from the multiverse. So from the conventional stats point of view, either hypothesis 1 is true or hypothesis 2 is true. Under a Bayesian view, hypotheses represent random variables that have probabilities. It's weird. It's certainly different. So what we want is, what's the probability that, say, the null hypothesis is true? That's the way we want to formulate it. This is again the formula for Bayes' theorem, and I just wanted to show you that, or remind you when we look at this, that the probability of the data given the hypothesis is the likelihood. So there's a close connection between likelihood and Bayesian probabilities, okay? So this is the likelihood of H1, and this is the likelihood of H2. And so what's different between, you know, an ordinary likelihood ratio and a Bayesian posterior probability is the prior. So you can think that where likelihood becomes posterior probability is when you can specify a prior to the hypotheses even before you collect the data. Okay, so Bayesian inference, on account of this, is pretty different from what we do, at least conceptually. The prior probability represents the investigator's information or strength of belief about the hypothesis or about the parameter value. The posterior probability expresses how the investigator's beliefs have been altered by the data, how that information has changed. Mathematically, the hypothesis or parameter is treated as though it's a random variable that has a probability distribution. That's the prior, and also then the posterior. So, I don't know if some of you have used a particular computer package called Structure. So Structure is a package where genetic data are obtained, and then it is used to determine the posterior probabilities that the data represent data from a single population, or two populations that are genetically distinct, or three populations that are genetically distinct, or four. So Structure is a method that uses prior and posterior probabilities to make statements about the strength of evidence that the data are from, you know, one species or two species or three species. And that's such a complicated way of doing things that I'm going to do the same thing, but using a very simple data set, just one variable, so that you get the idea of how the methodology works. So, not long ago, a couple of people here, this was a case of citizen science with Jen Gao and Michael Jackson, who is a biologist who lives on the Sunshine Coast, went to Nelson Island. Michael Jackson had asked Don McPhail whether he'd ever trapped any of the lakes on Nelson Island to determine whether there are two stickleback species in any of the lakes there rather than one. And McPhail said he went there once, but the natives were unfriendly, and he fled in fear of his safety. But anyway, Michael Jackson knows everybody, and now one of those former itinerants on Nelson Island runs a boat, and he took Jen and Michael there, and they threw a trap into a few lakes, including one lake called Little Quarry Lake, and they brought me back the fish from there. And here's the frequency distribution of gillraker numbers that I observed when we measured the fish from this lake. Again, this is an ultra simple case that I'm showing you primarily just to give you an idea of how this works. So there's the frequency distribution of gillraker number, and what we know from everything that we know already is that gillraker number has a unimodal distribution within a single species. And so the question then really becomes how many clusters or how many modes are in this distribution. It's very similar to what you would do with a far more complicated genetic data set if you're running the package called Buster. And so what we would like to know is, are there two species in this lake, or are there one species? Is there only one species in this lake? And we can formulate this as a Bayesian probability statement. What's the probability that these data are from two species rather than one? Well, that's a Bayesian probability statement, because either there are two species in this lake or there are one. The only thing that's left for us to determine is how much information we have about the two. There's no random trial, really. So in order to do this, we're going to make some assumptions, and one is that, based on the evidence we know already from other lakes, that the distribution is approximately normal. So for hypothesis that there is just one species in this lake, we fit a normal distribution to these data. We calculate the likelihood, the probability of the data given the hypothesis that there's just one species. Okay, and so it's possible to do that using the probability density equation for the normal distribution. And then we can repeat a similar calculation for the alternative, or the hypothesis 2, that there are two species in this lake, and that involves fitting two normals, one to one cluster and one to the other. We don't know where the clusters are. We ask maximum likelihood to find us those clusters as best it can. And here are the best fitting normal distributions, and we can calculate the likelihood, the probability of the data given that there are two species, as this. And so we have our likelihoods. What we want now is to convert this into a Bayesian probability statement, but to do that we need a prior probability. Okay, so we plug these likelihoods in the Bayes' theorem, calculate the posterior probabilities. Oh, but what should the prior be? What should the prior be? Well, here are the different probabilities that there are two species in the lake, depending on what that prior probability is. And again, I just wanted to show that the posterior probability does depend on the prior. So if we just say, well, we have, this is what's called a flat prior, an uninformed prior. We don't know anything, so yeah, let's just say 50-50. It's hypothesis 1 or it's hypothesis 2. That's the prior. In that case, there's two species in this lake. I'm certain of it. But how many species, or how many lakes in BC really have two species in them? Really? And the answer is, it's incredibly rare that a lake has two species of stickleback rather than one. Why don't we use a small probability as our prior, given that this was just some random lake and it hadn't yet been sampled, but there was nothing about that lake in particular that caused us to go there in the first place. There was no other evidence really that we had before we went to the lake that something might be there. And so, given that only 5 in 1,000 lakes in BC, or really only 1 in 1,000 lakes in BC have stickleback, let's call that a species pair. Let's just call that our prior. What's our posterior? It's not looking so strong anymore. Okay? I want to show you another application and draw another conclusion from the example.
Sorry, could you just describe the flat prior again?
Oh, a flat prior is, I'll show you again why it's called flat, but it means it's the uninformed prior. And it's typically used in Bayesian analysis of data whereby you assume that you have no prior knowledge whatsoever. And so basically, if you have two hypotheses, it's 50-50. Each of them has probability 0.5. It's kind of the no information prior. And that's standard practice in analysis of data, Bayesian analysis of data. So here's an example, okay? So I dug this up from a journal where they were, some new species of bee was discovered and they wanted to know something about the sex ratio, the fraction of individuals emerging from this colony that was male and that was female. And let's say, as part of this study, we want to estimate the proportion of males emerging as reproductive adults from the colony. So we know how to estimate a proportion. We've done it before. We know how to use likelihood. Now I want to show you how this would work if we're using Bayesian methods, which goes beyond likelihoods because it has a prior. So to begin with, we need to come up with that prior. So that proportion of males emerging from this brand new bee species, it could be 0 males, could be 0.2, 0.4, could be anything. And one convention that's used a lot in data analysis, Bayesian data analysis, is to express the prior in terms of total ignorance. It could be anything. The probability density is just completely flat and equal across the range from 0 to 1. So that's the non-informative or flat prior. But come on, we already know, like we have this wealth of data out there which says that typically the sex ratios of populations are close to 50-50. We have a theory that predicts a 50-50 sex ratio under most circumstances. And that's usually what we find when we go out into nature and estimate the fraction of males and females in a population. One of the often stated advantages of using Bayesian statistics is that the priors can make use of prior information. Not just, we can do better than flat priors. We can make use of all the wealth of evidence that's accumulated so far and use that in coming up with our posterior distribution. So here's a candidate distribution that takes into account the fact that usually we find something close to 50-50. So why don't we express that in terms of our prior? Well, I forgot to tell you one thing about bees, and that is that typically sex ratios of bees are female biased, and that there's a wealth of data out there, and in fact there's theory out there that indicates, based on kin selection, why this expectation is sound and why sex ratios are typically, it's because of the way sex is determined in the Hymenoptera, in social Hymenoptera, and that it relates to the fact that the workers, being all female, are actually more closely related to females, their sisters, than they are to their brothers. And so if the workers have control over the sex ratios, we'll see female biased, and often the workers did have control. So maybe we should use this prior, which takes into account even more prior information than the previous case. Okay, so here are the three cases, and here are the maximum probability estimates of the proportion of males in those three cases. So I just looked at a small data set of 18 individuals, say, which they collected from on one day. And in green, I've shown the three priors that I just went through. In blue, I've shown the likelihood, which is the same in these cases. And it's the product of the likelihood and the prior probability that determines the posterior probability, which is shown in red. When you can't see the blue, it means that it's behind the red, but it's exactly the same. And that typically, frequently happens, depends on the circumstance, that when you use a flat prior, the posterior probability matches the likelihood function. Okay, so again, I want to show you how estimation works in a Bayesian framework, and how prior probability might influence the estimate that you obtain, or could influence the estimate that you obtain. Okay, so just to sum up, the estimate having maximum posterior probability, so rather than the maximum likelihood estimate, now we're getting the maximum probability estimate. And that depends on the prior. And that's, again, long been a source of controversy in the literature. What prior should we use? So one resolution is that we all decide from now on to resolve all of the arguments about priors, that from now on we're going to use non-informative priors. Well, that's kind of disappointing, because this prevents us from incorporating prior information, which is thought to be one of the virtues of this approach, and a weakness of conventional null hypothesis significance.
Can't you use multiple priors?
So, I mean, that I think is sensible, and I'm going to show you what happens in that case. But I've shown you three. So I guess here's an example of the use of multiple priors. And the results don't agree quantitatively, but they're not far off. And I guess how to approach this in this case, the strategy would be to try different priors and see if it makes a difference. And that's what I'll show shortly. But I wanted to first show you how, remember how you calculate the likelihood-based 95% confidence interval using the likelihood function. I also stressed earlier that the likelihood function is not a probability distribution. Okay, now it is. This is the this is the posterior probability distribution. If we just completely throw away our definition of probability out the window and accept an entirely new one, we now define the variable that we're interested in looking in, the proportion males, as a random variable. And the way to get the equivalent of a 95% confidence interval, here's the maximum posterior probability. So basically just lower this line down, 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 until you reach a point where between this line drops down to the x-axis and this one includes 95% of the area underneath the posterior probability distribution. So we'll be doing an example of this in lab this week, in the workshop on Friday. And one of the data sets that we're going to use is the elephant data set, which we used earlier in the likelihood workshop. And so what I recommend strongly is that you redo that one, that you go back and redo that one just so that you remind yourself how likelihood works. Because then what we're going to do is we're going to take it to the next level. We're going to redefine probability and we're going to go there. Okay, and what this region is called is the 95% credible interval. That makes sense. Probability is a degree of belief. This is basically where 95% of our belief lies regarding the value of that population proportion. And the likelihood-based 95% confidence interval I'm showing you here for comparison, 0.19 to 0.62. The 95% credible interval under the flat prior turns out to be actually very close. And I think that's often and perhaps usually true, that if you use a flat prior, likelihood and Bayesian statistics actually gives you a fairly similar result. But I want you to dwell a little bit on the likelihood interpretation and the difference from the Bayesian interpretation of what that interval actually means. Under the likelihood interpretation, most plausibly p is between 0.19 and 0.62. In repeated random samples taken from the same population, likelihood-based confidence interval will calculate each time will bracket the true population proportion p approximately 95% of the time. That's our conventional definition of a 95% confidence interval in the world where probability is defined as a long-run proportion. But in the world where probability has a completely different definition as a measure of degree of information or belief, but probability is 0.95 that the population proportion lies between 0.2 and 0.61. And the reason this is so different from this one is that here, p is out there, it's truth, and our uncertainty is from the random sampling process. Here, p, the proportion of males, is a random variable. This model is a random variable. So it's not the case that there's a true population proportion in that new species of bee. The fact is that the true distribution, the true proportion of males in that population has a probability distribution. And it's not until we collect data that probability distribution changes. That's how a prior becomes a posterior. But I do want to point out one thing, and that is that, in fact, they had a much larger sample than I used in my work-through example previously. And the basic result from this is that I get the same answer regardless of the prior. And the basic message from that is that with lots of data, the prior doesn't matter that much anymore. And that's regarded as one of the saving graces of this approach. But the flip side of that is that if you don't have much information, the prior matters a lot. And so if you're trying to determine whether, say Saddam Hussein is building weapons of mass destruction or not, and decide whether or not on that basis to invade the country, your prior probability, when you lack data, the prior probability has a great influence on your posterior probability. So I want to talk about one more thing, which is Bayesian hypothesis testing, using something called the Bayes factor. And there have been some recent papers on this topic as a way of maybe resolving the debates and the differences between null hypothesis significance testing and Bayesian statistics. So Bayesian methods can be used to quantify the strength of evidence for one hypothesis relative to another using something called the Bayes factor. Okay, so it's presented as a Bayesian alternative to null hypothesis significance testing, but I'll show you later that there's a resemblance between the two. Okay, so within the Bayesian framework, one can calculate the weight of evidence for one hypothesis relative to another, given the data. That's the posterior probability. And the Bayes factor can be used to summarize that weight of evidence. So for example, here's our two-sample t-test scenario. We have two groups, and we want to know whether the mean difference between them is 0 or not. Under conventional null hypothesis significance testing, the null hypothesis truly is that the difference between mean 1 and mean 2 is exactly 0. It's not 0 plus or minus epsilon, it is exactly 0. It's not an approximation, it is how we calculate the p-value. The alternative being that, who knows what it is, but it's not 0. Which is regarded as one of the problems with null hypothesis significance testing, that we're not actually comparing against a sensible alternative. Okay, so the one difference between Bayesian hypothesis testing and conventional null hypothesis significance testing is that there's no precedent. Under null hypothesis significance testing, only one of these two hypotheses is tested, and that's the null. It's under the null. Nobody cares what this looks like. It's under the null that you decide or that you calculate p. And really, it's only the null that's being tested. Whereas in a Bayesian framework, it becomes possible to say, well, neither of them has precedence. Maybe it's 0, maybe it's not. What does the weight of evidence say in favor of one versus the other? So there's no longer any need to specify, we're going to assume that 0 is true, and only if the evidence convinces us otherwise will we finally say, okay, no, it's not true. But to use Bayesian methods, of course, you need to use a prior. And the Bayes factor, once the data are observed and you've calculated the probability of the hypotheses given the data, the Bayes factor is the ratio of the posterior probabilities for one versus the other. And so then the question is, what's the prior probabilities? So how you actually calculate the probabilities of the data under the alternative hypothesis is a little complicated because it includes everything but 0. And I'm not going to go into that. There are ways, because we have to integrate over the whole range. But the basic idea should be straightforward. So if the two hypotheses H0 and HI have the same prior probability, and by that I mean, let's just say that we have no information, we don't really have any reason to believe that H1 is true or H2 is true. We have no prior evidence for thinking that the null hypothesis is true or that the alternative. So let's just say, 50-50. If that's the case, then the Bayes factor is just the ratio of the likelihoods. The probability of the data given H1, the probability of the data given each together. And then the Bayes factor at this point is treated much like, a difference, an AIC difference, where we say, well, a Bayes factor of 1 to 3 is considered not very strong support for the alternative hypothesis. So if the posterior probability is only about 3 times for HA than for H0, then we say, well, that's not very strong evidence. There's a little bit of evidence in favor of the alternative, but not much. A Bayes factor of 3 to 10, let's consider that substantial evidence. And then a factor of 10 to 30 is considered strong evidence. So those are kind of brackets, and again, like AIC difference, if we were going to use this approach, we would have to all come to agree on, what constitutes strong support, substantial support, and so on. And again, those are the kinds of agreements that we have done already in coming up with 0.05 as the conventional cutoff for null hypothesis significance testing. So I see no reason why we couldn't all come to an agreement about what we consider strength of evidence. So what this graph shows is the results of an analysis in which Wetzels et al. Went to the psychology literature and extracted from the psychology literature 855 two-sample t-tests. And then based on the data that they extracted, they analyzed the data in the conventional way, using a standard p-value. And they analyzed the data using Bayes factor, which is shown along the y-axis. And lo and behold, they're so strongly correlated with one another. So all this philosophizing about the difference between null hypothesis significance testing and Bayesian approaches, the fact is that the outcome, the p-value on the one hand and the Bayes factor on the other, are incredibly tightly correlated. I mean, I would want to see this repeated in ecology. This is psychology, right? They're totally different. You know, we want to see it repeated in our own field, but it would be interesting maybe to do that. But when I saw this graph, I thought, I was blown away. Like, I had no expectation that P in Bayes factor would be so, because this is, you know, according to the Bayesians, this is good science, this is bad science. And yet, they're correlated. So what do you make of that? But, and here's the clincher, how much support is there for the alternative hypothesis associated with a p-value of 0.05? They're strongly correlated, but let's just look at the strength of evidence that comes from one approach versus the other. Under the Bayes factor approach, 0.05 constitutes almost, like scarcely, stronger support for the alternative hypothesis than the null hypothesis. So even though these two approaches are yielding strongly correlated results across all these studies, where they differ is in the cutoff for deciding what's evidence and what's not. 0.05 is ridiculous. Basically, as far as Bayes factor is concerned, represents only anecdotal evidence at best. And it's not until you start reaching p-values of 0.001 that that you produce a result that, in a Bayesian context, constitutes strong support for the alternative hypothesis. So this isn't entirely resolved, but the upshot of these analyses has been the most important thing we have to do is not null hypothesis significance, Bayesian testing. The most important thing we have to do is revise our standards. Know what constitutes evidence. And so that's the debate as I understand it. So you can comment on that. Here's one salvo that came out in PNAS and generated a whole lot of heat. And I guess that's the question I leave to you, because I don't know how to answer this, and that is, should we revise the standards that we use to decide what constitutes evidence and what not? I don't have time, but there's Bayesian model selection, BIC instead of AIC. I have a few comments about that here. You've already seen maybe BIC in your analyses. It spits it out, and you might have wondered what it is. Here it is. Summary. Bayesian probability is different. Bayes' theorem can be used to estimate and test hypotheses under this alternative framework. It requires prior probability. The influence of the prior declines with more data. So get a lot of data, whatever you use. The interpretation is different because the definition of probability is different. The interpretation of 95% confidence interval or credible interval. Bayesian hypothesis testing using Bayes factor suggests that above all else we need to raise our standards. And ecologists are facultative Bayesians. You'll see Bayesian analyses used in the journal Ecology, even in combination with null hypothesis significance testing, as though they meant the same thing. Next week, we're going to talk about hypothesis testing a little bit more, but the idea of going out and when you do an experiment or an observational study, actually going out with more than one hypothesis. And looking for presenters and moderators. So you may step forward, or you may let R push you in my direction. And if you would like to do this, just come and see me now.
A couple of
Oh, thanks.
I don't even